Okay, another example of a hypothesis test. We haven't done a two-sided hypothesis test yet, so this is an example of a two-sided hypothesis test for a mean with a known population standard deviation. All right, so in this situation, we're looking at wheat crop damage by hail, and it doesn't matter what the situation is, all we are concerned with are the numbers that will allow us to perform the hypothesis test. So we're going to say nationally, about 11% of the US wheat crop is destroyed by hail. So that's the idea going in, okay? That's the null hypothesis, that the national average is 11%. Some insurance company is studying wheat hail damage in Colorado, and they take a random sample of 16 claims that gave the following data. These are percentages of wheat crops destroyed on different farms. Okay, so 15% destroyed, 8% destroyed, so on. So we have a sample of 16. Now, because that sample is small, we have to assume the population distribution is normal. We're going to make that assumption, and we're going to assume that we know the population standard deviation is 5%, and we're being told to use a significance level of 0.01. And we want to test whether the true mean is different from that hypothesized mean of 11%. So we want to see if the hail damage on the wheat crops in this place in Colorado is different than the national average. We don't know if it's going to be higher or if it's going to be lower, so that's why we're going to look at both ends and see if there's any difference at all. Now, the thing that changes here comes in the third step, the p-value. We'll get there. But the first two steps are exactly the same. We set up the hypothesis, the unknown population mean, we're going to say is the national average of 11%. Right? Against the alternative that it doesn't equal 11%. So that doesn't equal, notice it's not a less than sign, it's not a greater than sign, so that's why we call it a two-sided test, and we're using an alpha level of 0.01. We go to our second step, and we form our Z test statistic, right? This is a Z test statistic because we know sigma. So we know how to calculate that, the sample mean minus the hypothesized mean over the standard error of the sampling distribution. We have all those values from our gathering of the info. 16 is the sample size. Hypothesized mean is 11%. Our sample mean, we got a sample, we got to get the sample mean. That's very important. We took the mean of these 16 values. If you put these values into your calculator and divide by 16, you're going to see that the average is 12.5. So obviously we need that sample mean. We weren't given the sample mean in the problem, but we were given the actual sample data, so we can come up with that sample mean of 12.5. And we are told that the alpha level is 0.01 and our sigma was 5%. All right, so we have all those numbers. We plug those into the Z statistic formula, and we round to 2 decimals, and we get our Z statistic of 1.2. So again, remember what that tells us. That tells us that if this is true, if the actual population mean is 11%, then we are going to get a value like this from a sample of 16, an infinite number of samples of 16. We're going to, this 12.5 is 1.2 standard deviations above what would be the center of that sampling distribution. So not too far away from center. Well, how often is that going to happen? What is the probability that if the null hypothesis is true, we're going to get a value this far away? Well, now this is where the two-sided alternative affects us. Because we don't know what side of the distribution we're looking at, we double the probability of finding something as extreme or more extreme than what we found in step 2. Since step 2 gave us a positive z-value, we're looking on the right-hand side further to the right of 1.2. If this was a negative value, then we would be looking at the left-hand side of the standard normal distribution and looking for the probability of getting something more extreme than what we found. So the p-value is the probability of finding something more extreme than what you found in step 2. So this is a positive number, so more extreme is going to be even further to the right. And we double that because it's a two-sided test. Okay? So twice the probability that z is greater than 1.20. We know how to find the probability that z is greater than 1.20 in our standard normal table. We can look up the probability that z is less than the negative of that number using the symmetry idea. When we look up the number z less than negative 1.2, we get this value. We double that value, and this is our p-value. Right? Very high p-value, right? So again, what this is saying is that if this is true, we're going to get a sample mean from 16 values this far away from that, well, 23% of the time. Not that surprising. Almost 1 out of 4 times, we're going to get a value this far away from this, even when that's true, from samples of size 16 in this area of Colorado. So the p-value is much greater than alpha here. And remember our condition for making a conclusion. If the p-value is greater than alpha, that means we do not have sufficient evidence to change our mind. So we do not reject the null hypothesis, and we say there is not sufficient evidence to suggest that the wheat crop damage percentage in this area of Colorado is any different than the 11% national average. All right, so same 4 steps. The only thing that changes in a two-sided alternative is you double the p-value. If you're whether it's a z statistic or a t statistic, we're going to double the probability in step 3 because it's two-sided and we don't know what what end of the distribution we're looking at. Same 4 steps. State the hypothesis, find the test statistic, whether it be a z or a t, calculate the p-value, make a conclusion based on the p-value and the alpha level. Okay, we will do more examples as we move along.